Well, good morning to all of you, or good afternoon if you're in the afternoon lab session. It has been far too long since our last video podcast. So, coming at you with a healthy dose of bedhead, we're ready to talk about the periodic table, something that you already know quite a bit about. There are only a few new concepts that I put in here, and as I look at my notes here, my paper copy, I know it's 2 pages, but it'd be 4 as we print it out on the good old printer. And we'll get after it here this morning or this afternoon, depending on when you're watching this. Really, there are a few things on the front side here that I want to make mention. I think anybody who's taking high school chemistry should be very familiar with who Mendeleev is, because he's the one that we credit for our current periodic table, because he left blank spaces for undiscovered elements, which really is quite remarkable when you think about it, to say, hey, I'm going to leave a spot here for something that's not been discovered. Very, very surprising, courageous almost in that sense. And it turned out that he was right, so that's why we kind of talk about him. If he were wrong, we probably would say there was a crazy guy who was so arrogant that he left blank spaces for things. Groups and periods, again, by now where we are, I would expect all of us know that groups are vertical, periods go left to right. Okay, periods do talk of a little bit about valence shells, that outermost energy level, and it would probably be helpful while you're going through this if you have a periodic table handy. I know I've got several, never seem to be without a periodic table, just for the fun of it. Common group names, back in September or probably August, you got a colorful sheet of paper there, or different zones of the periodic table. Those are the ones that are most important. I know we've just done the electron battleship business last week in the chemistry lab time, so I'm sure that you're very good with the electron configurations. What we're talking about here for neon, I'm just going to go through a couple of these: 1s2, 2s2, 2p6. And if we look at argon, argon would certainly be 1s2, 2s2, 2p6, 3s2, 3p6. Okay? And normally we would go through the long form, but I also want you to see, well, I'll do one quick example here. For silicon, what I have would be a 1s2, 2s2, 2p6, 3s2, 3p2. And what I want to point out here is, as we deal with this shortcut form, which I think you're already probably pretty familiar with, what we're going to do is we're going to say, you know what, silicone here, all of those electrons that I've highlighted, those are the exact same thing as what neon has, a neutral neon. So what we do is, for the shortcut form, I'm going to say, you know what, silicon would be known as neon's electrons, and then add 3s2, 3p2 for the final answer. Okay, and in a very similar way, we know that potassium goes clear out to 4s1. Okay, 4s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Well, that's actually all of argon plus a 4s1. So, not surprisingly, potassium would be argon, all of the electrons of argon, and 4s1. Okay? So, please take a moment and see if you can crank out these two additional examples here. And I know Miss Waits will have the answer key, and she's all good with this material, so I don't want to spend any more time on that. Okay? You'll also be able to do these, I think, without any difficulty. Again, if you've played the Electron Battleship game, you are rocking and rolling all over the first page of the notes. Okay? Let's move on to some more challenging material. There are some trends that we do need to memorize in the world of chemistry. And some of these trends are very easy, and I know that they're easy because when I asked you questions last week about size of atoms and so forth, people get these things right. So not a lot of a big stretch this time. This wonderful graph here that I'm looking at and you're looking at, a beautiful color arrangement. Sorry that it's not colorful on your notes, but oh well. As we go down, this is not surprising at all. As we go down, things get larger. They get larger because you have more energy levels of electrons, more energy levels. So it's really no doubt that as we go down the group 1A, I see a small lithium, a larger sodium, an even bigger potassium, rubidium gets larger, cesium's even larger than that. More energy levels of electrons, 1s1, 1s1, 2s1, 3s1, 4s1. They get larger and larger and larger. Okay. Now the horizontal trend, that I remember as being a little bit more challenging to see. That is going across. Okay. And you can see just from the graph here, and as I'm looking at it here. That's me. Okay. As I look at this from one side, left side to the right side, I see that things get smaller. And it's one thing to be able to memorize and say, oh yeah, they get smaller, but I think it's important that we know why they do get smaller. Okay? As it says down here, well, let me move that up. If we consider the horizontal trend, which is harder to see, it says here that the atoms get smaller going across. But why is that? If we add protons and electrons to the same energy level, okay, those protons are pulling in the electrons with greater attraction. Well, that's what it says, but let's see if we can examine these things, okay? If we look here at a small lithium and a giant potassium, okay, if we look at the electron picture here, and this is where, if you can do the battleship game, about 80% of this unit is all set for us. If we look at little lithium versus the bigger potassium, we clearly have more energy levels, and so it's larger in size. Okay, there's not a whole lot more to add to that. Okay, but where it gets a little bit tricky is if we consider a big old lithium, and it's relative in its size, and a tiny fluorine. This is a situation that I want to spend a minute or so talking about, because I know it's written here, okay, it's written there, but that doesn't mean that you understand it. If we visualize 3 positive protons, okay, 3 positive protons here, and we're dealing with kind of like a rock concert, if you will. We have a 1s2 and a 2s1. What I'm going to do is I'm going to draw in kind of like it is a rock concert. And that's what it looks like there. And if I put the electrons in, I've got 3 electrons. 2 electrons go in the front row, the 1s2 electrons, and then 1 electron goes in the outermost energy level, the second energy level. Well, 3 protons pulling on 3 electrons. There it is. That's one way to think about it. And then if we look at fluorine over here with 9 protons, and I will take a moment to draw all 9 protons, and I would suggest you do the same. I think it's kind of fun. Okay. Well, if we then switch and we say, well, it's also pulling on 2 energy levels. Well, the 2 energy levels, okay, the 2 energy levels are going to be closer to the 9 positive protons, okay? And it has 9 electrons, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons, okay? The key to recognize is that the 9 protons are pulling on 2 energy levels. And what we're talking about there with the 9 positive protons pulling on those energy levels, it's similar in the respect that if these were all magnets, you would be pulling those electrons, these electrons would be pulled in closer because of that greater positive charge. Okay? I remember when I first learned this, I was thinking, hey, over here I've got 3 pulling on 3. I've got 9 pulling on 9. That's not the right way to think about it. Instead, what we want to think about is I've got 3 over here pulling on 2 energy levels. Over here, in the case of fluorine, I have 9 protons pulling on 2 energy levels. Okay? So if we think about energy levels, not number of electrons, I think that's the key to being successful here. Okay? So that takes care of atomic radius. And I want to stress atomic, that's where it's neutral. We know that atoms are neutral. Neutral atoms. Okay? I know it says that, but sometimes it's helpful to hear somebody actually say it out loud. That's in contrast to the ionic radius. Now, an ionic radius, we know that there are positive and there are negative ions. Positive and negative ions. Yes, we call them cations if they're positive. Okay? Cations are positive. And we know that anions, not anions, but cations are positive, anions are negative. If we look here, and this really, again, if you can do Battleship, you're ready for the periodic table test. If we look here at a bigger sodium atom, since it's neutral, okay, look at the teeny tiny sodium ion, sodium cation in particular. And if we look at what's going on with the electrons, there's the electron picture. If it is neutral, and when we form that ion, boom, that one goes away. That one goes away. So what we have is the electrons end at 2p6. And so the loss of an electron, the loss of a negative electron, which produces a positive cation, okay, results in the ion being smaller because we're losing the outermost electrons. So the cation is smaller than the neutral element. Okay? The neutral atom is larger than the positive cation. If we then consider the example of what if it goes the other direction, the anion, there is my neutral fluorine, 2p5. Well, we know that fluorine has a very high electronegativity. It is going to take an electron to become the much larger 2p6. There are more electrons now, just one more, but nonetheless, it's gone from being neutral to -1 by adding that negative electron. Since we're gaining electrons, it's going to become larger in size. Okay? And that's, again, once you know how to think about these things, it really, really is quite simple. Ionization energy. Ionization energy is something that I've always thought that they should call it cationization energy, because it's the energy needed to make a cation. The energy needed to make a cation. So we're always pulling out an electron. We're always removing an electron. And we know that ions could form when we gain electrons or when we lose electrons, but ionization energy is all about forming cations, pulling, yanking away electrons. And an interesting thing happens if you understand the basic electron picture with an electron configuration. Everything makes sense. And here's what we're talking about. And with my periodic table in hand here, I'm looking right now at a glorious sodium metal ion here, or sodium atom rather. What we're talking about, sodium, okay, and I'm not going to do this for each one, but sodium, I'm going to write it out, 1s2, 2s2, 2p6, 3s1, okay? As I look at that, here's what I see. I see the first energy level is full. I'm going to wall it off, okay? The second energy level consists of 2s2 and 2p6. That is also basically locked in a box. Then we've got the 3s1, the 3s1 electron. Here's what we see. If you would like to take the 3s1 electron, go for it. It'll cost you a little bit of energy, 496. Okay? 496 kilojoules per mole is the cost for that electron. If you want to, oh, don't do it. Do not do it. You don't want to do it, but if you have to, if you want to crack into this stable octet, if you want to crack it, if you want to disturb the 2s2, the 2p6, you better bring your wallet because it's going to be expensive. And what we're talking about here, to yank out the second electron, to pull the second electron will require almost 9 times the energy that it took to take out the first one. Holy good gravy boat. We're talking that's expensive because you're disturbing a full valence shell, and that's expensive. The first electron, you can have it. It's extra. We don't need it. But to disturb a stable octet costs a lot of energy. The third electron, you are continuing to disturb that stable octet. That's going to cost you even more money. Okay? And what we can do as we look at this, as I erase that clutter, okay, if you can do the electron configuration, and again, I'm just going to look at my periodic table, and I would encourage you to look at it as well. I see that magnesium is right next door to sodium. Magnesium has 2 valence electrons. It's in group 2A. So that tells me that magnesium, and if we want to use the shortcut form, magnesium would be, I'm looking here, that would be neon and 3s2. So I look at this and I say, you know what, I have 2 extra electrons before I disturb a full valence shell. So it's not surprising to me when I look at this and I say, well, that first one of magnesium is going to cost you. The second one will cost you more. But oh my goodness, it's like 5 times the cost. That is crazy. To disturb the full valence shell of neon is expensive. It is expensive. So you don't want to do that. So we see this big jump in terms of energy cost whenever you try to disturb a full valence shell. I look at potassium. Potassium is a 4s1, and so potassium, you can lose 1 electron easily, but it's going to cost you more, a lot more, 7 times more if you want to disturb the full valence shell of potassium. Calcium, similar. There are 2 valence electrons, so the first 2 aren't bad, but boy, you pay a big energy cost on that third one. Okay, so hopefully this tells you what you can see here. I also want to make mention since we're talking about, as I get rid of the clutter here, since we're talking about the trends of the periodic table, I do want you to compare, say, sodium to potassium. Again, as I look at the periodic table, I see sodium is a smaller atom than potassium. Okay, 3s1 compared to 4s1. But what I see here is the price that you pay for the first energy, or first electron. If we're looking here, we see that it is cheaper, or requires less energy for potassium than it does sodium. And that's consistent with, if you want to take electrons that are close to the nucleus, you pay more in terms of energy. If they're farther away from the nucleus, they don't cost as much. And so that's why you see that this is more expensive in terms of energy. That's a pretty pathetic dollar sign. That's more energy for that than for potassium. Okay? So again, to me that makes sense. Then I wanted you to see it, ooh, gravy boat. I wanted you to see it graphically here for carbon. Carbon, again, to me it just seems so logical. For carbon, we're talking 1s2, 2s2, 2p2. So I look at this and I say, well, that is a full energy level there, 1s2. I have 4 electrons to give that probably won't require a lot of energy, but then if you try to crack into the 1s2, it's going to cost you. And so we see the first electron out, okay, the second electron out, the third electron out, the fourth electron out, and the big jump is when you disturb the valence shell there. Okay? So we're in pretty good shape there on that. Big jump would occur when you try to take the fifth electron out. That 1, 2, 3, 4 can be lost, but boy, when you try to touch the 1s2, you're cracking a full valence shell. Okay? Alrighty. Anything worth doing is worth overdoing. And so as we look at this, again, it's more of the same, but nitrogen would be 1s2, 2s2, 2p3. Again, 1s2 is full, boxed up, locked in a box. I have 5 electrons that you might say are loose. 1, 2, 3, 4, 5. But boy, do you pay an energy cost if you want to disturb the 1s2 electrons on nitrogen. Okay? More of the same there. Basic definition for electron affinity. It isn't that popular or common of a thing that really is essential, but I put it in here for you just so that way you've seen it. It's really the opposite of ionization energy. Ionization energy involves taking away an electron. Electron affinity means putting an electron on. Okay? And the trend, fluorine has the highest, francium the lowest. Okay? And so basically, if that's my periodic table, that would be the highest in that corner, the lowest down here. Okay? And the trend for electronegativity. Electronegativity we have talked about extensively, and that's that rubber band demonstration, the ability of an atom to attract electrons to itself. Okay? And we've said all along that, and I'm going to attempt to draw a crown, and there's my king fluorine with the highest electronegativity value. Okay, the relative attraction of electrons by atoms. Okay, that tendency to attract electrons. Linus Pauling has gone through and he's assigned different electronegativity numbers to the different elements. There are some problems that people have with some of the giving a one-size-fits-all electronegativity to, for instance, every carbon in every molecule. But the numbers are out there, and you can see, again, the overall trend. We've got the lowest and we've got the highest. electronegativity value, and the trend goes across the periodic table as you can see there. Okay, well, hopefully this gives you kind of a quick summary of the unit. I know I've got some former AP exam questions that you'll be receiving. You've also got some multiple choice review questions, which I think are really quite good in the sense that they'll make you think a little bit and make you go over these notes. But I think you should be ready for an assessment on the periodic table, but we'll probably combine that with another unit. So, well, signing off. Hopefully all went well this period for you. And I guess we're right at 25 minutes, so there should still be plenty of time for you to crank through the multiple choice questions. Enjoy. It's been joyful.